Okay, hello, this is the last video lecture on semiconductor devices. We'll be talking about bipolar junction transistors, or BJTs. Okay, and so the first thing that we want to talk is why do we use BJTs? Aren't CMOS devices better? CMOS devices being MOSFETs, right? So why BJTs, right? We put aren't CMOS devices better? Right? And so we talk about the advantages. Right. Bipolar devices are inherently better in high-speed, high-gain applications. So that's the first advantage. High gain applications. Another advantage is that bipolar devices have higher breakdown voltages than CMOS devices. So let's write that. Bipolar devices have one problem that sometimes we find when we're using MOSFETs is that for the insulator, for the gate capacitor, that MOS capacitor that we talked about in previous lectures, if you put a voltage that is too high, you can experience breakdown and then the MOSFET gets permanently damaged, right? Well, for bipolar devices, that voltage at which there is breakdown is a lot higher. So that's another good thing, but the main one by far is this one. When you want high speed and you want high gain, sometimes the BJTs are the way to go. But of course there is disadvantages, and this is basically one of the main ones why most of the times we use MOSFETs, is because for BJTs there is a non-zero base current. Right? Okay, so now we're going to start talking about the basic operation of BJTs. So okay, so let's start off by drawing a simplified model of the NPN of an NPN BJT, right? So here's the NPN BJT. Right, and so we will label the leads, right? So you're gonna have a collector, emitter, and the base, and then this goes on to the following. So you have, this is the back-to-back diode model that a lot of times they use for large signal DC analysis. And so you got the base, emitter, and then collector, and then on the bottom we'll put a visual model of how the semiconductor device will actually look like, right? So it'll look something like this, right? And so a few things to note from these diagrams are the following. we have that the NPN device is asymmetrical. Okay. The second thing is that the doping concentrations are not uniform. And the last thing to note is that this device is basically two asymmetrical diodes stacked back to back. Thus, that's why we use this model here on top. So the NPN device is asymmetrical. This can totally be seen by looking at the device geometries for the different semiconductor types. The doping concentrations are not uniform. Here we got a lot of electrons. Here we just got a large concentration of holes, and here we got a low concentration of electrons. So that's true. That's true. And then the device is basically two asymmetrical diodes back to back. Of course, because you got PN junctions, right? One from here to here and the other one from here to here. Okay, so now let's talk about the story behind, right? So to be able to do that, we have to go a little bit deeper into the type of materials that are used for the semiconductor. So we'll have to look at the junctions themselves, the PN junctions, and how the depletion regions are generated. Right, so for that, let's first look inside the NPN device. So let's first look inside the NPN device. Okay, and so for that, let's draw a quick visual diagram. Okay, so here it is, and so let's know that we have a strongly doped material, like we said before, at the left side, right? An N plus material. Then we got just a material with a large concentration of holes, and then we got a weakly doped N-type material in this side, you know? Okay, and then here are the leads, the emitter, the base, and the collector. And as you can see, the depletion regions extend farther into the weakly doped material. So let's write that down. Due to the PN junctions, we have depletion regions. Extending further into those materials that are more weakly doped. But actually, to conserve charge neutrality, an equal number of dopant ions or fixed charges are uncovered on each side of the junction. What that means is that we can update our previous diagram to the following. So first we write down which yields the, so we take this one and we update it to the following. Okay, and we get the final model right here, where the number of charges on one side of the junction is equal to the number of charges in the other side, but the width of the depletion region depends on how strongly the material is doped, right? Like we have it right here. It extends farther into those materials that are more weakly doped, like we said here. Okay. Alright, so now we wanna do the same thing that we did on the other videos. We want to apply voltage bias to this BJT and see how it performs, right? So we say now let's apply some test voltages. Okay, so here's the diagram. Let's first look at the biasing conditions of this experiment. So we have base to emitter voltage of 0.7 volts. We have a collector to emitter voltage of 1 volt, right? And so let's write down what we see that is happening, right? As soon as we run the experiment, the following is what happens. So I call this the base to emitter junction, because that's the first effect that we're going to start talking about. So note, so due to the holes flowing into the P material, due to the positive potential that we're applying to the base, we get some holes going in here, and then they are filling the negative fixed charges, so they are filling these guys right here. Therefore, the width of the depletion region between the base and the emitter gets smaller. So that's the first thing that we want to write down. Due to the holes flowing into the P material, filling the negative you can also think of as the electrons as the ones coming out, right? As the electrons come out, they leave holes behind, right? And those holes are used to fill the negative fixed charges, right? And so we get smaller depletion region. And the width of the depletion region, in this case W1, becomes smaller. Okay, so that's the first thing that we see. Now the second thing is that the carrier concentration gradient increase. The differential in concentrations of carriers increase, meaning that we have a lot more holes in here than we had before, right? And we had very few holes in this side, which means that we're gonna get holes diffusing over to this side, or you can think it also in the other way, since you have electrons, you got a current flowing this way, so you got a lot of electrons in this side, and you got very few in this side, right? So due to this differential in concentrations, we get, through the process of diffusion, which we talked about it before, we get current, diffusion current, that's flowing this way, if you think of current as the flow of electrons, or this way, like you normally think of a positive charge flow, then this is the normal way of current flowing. Okay, and so let's write that down. So as the width of the depletion region, the omega 1 becomes smaller. The carrier's concentration gradients increase. And electrons, I'm going pretty fast over some of these concepts because I explained them before in the other videos, which were pretty long. So this one is the third one, so that's why I'm going a little bit fast. In the other ones I talk a little bit about how the diffusion process actually works, drift process for carrier motion, plus material to the P material. Very simple. That just means, so that is the PN junction is forward biased. So the PN junction from base to emitter is forward biased. Okay, and so this is a huge point. This current represents the small base current of BJT devices. Right? That forward bias junction represents that current. Okay, but now there is something that we have to take into account. There is a huge point that we have to consider, and it is that the size of the P material and the doping is very small, right, compared to the N plus material. So the number of holes in the P material is a lot smaller than the number of electrons in the N plus material. What that means is that a lot of electrons are coming to the P material but have no hole to fill. So they start to become minority carriers in the P material, just like if they were thermally induced electrons. So we have a very small base current, but we're going to have a very, very large collector to emitter current, right? And that's going to be due to these minority carriers that are induced here in the P-type material. Okay, so let's write that down, because I know it was pretty long. That's why I like to write it down so that I time myself. Of the P material and the doping are very small compared to the N plus material. So the number of holes in the P material is a lot smaller than the number of electrons in the N plus material. Therefore, and here is the huge point, a lot of electrons are coming to the P material but they have no hole to fill. So they start to become minority carriers. In the P material. Just like if they were thermally generated electrons. Okay, so now we want to talk about the base to collector junction, right? Because that's where the interesting part comes in, right? So that the next thing that we're going to do is that we're gonna redraw and we are going to talk about the next effect, which is the effect of the base to collector junction. Okay, so now we run the experiment, and what do we see that is happening? Note that since we apply a positive voltage here, what's happening is that all the electrons that are in this material are gonna want to go over this side, right? Are getting pulled that way, correct? So they are uncovering all these positive charges, right? What that's doing is that it's basically reverse biasing this diode right here. Or you can also think as widening the size of the depletion region, right? So let's write that down. And we know from our previous lectures that what that's going to generate is a huge electric field pointing from the collector to the base. So we'll write that down. Since we applied a positive voltage at the collector, electrons quickly start rushing out of the N- material, leaving behind that's not right, behind a new positive fixed charges right here, and thus we end up with a wider depletion region. With a wider depletion region, and that's W2 right here, and a huge electric field. Pointing from the N- material right here or the collector to the P material. It's actually better to say, because the electric field is not really from the collector, so it is better to say that it's pointing from the inside the N minus material over to the P material, as it is actually in the depletion region that we have this huge electric field. Okay, so now tying things up. This is a very important section here, because we take both of the effects that we talked about, and using them we describe the behavior of the BJT. So we say, remember the minority electron carriers that were generated in the P material, or induced in the P material. Remember from the base to emitter effect that were diffused from the N plus material. Well, that's gonna fit in nicely, because as the minority electron carriers in the P material start to increase, we get a lot more electrons in here, they are strongly pulled towards the N minus material, right? Remember, we're talking about electrons here, right? So they are going to be pulled very hard by this strong electric field, which is pointing in this direction, right? Since they're electrons, they're going to want to flow in this direction, right? So if they find themselves close to this region, they're going to be sucked to this side, right? So let's write that down. And start to increase. They are strongly pulled towards the N minus material, strongly pulled this way by the strong electric field in the depletion region. Okay, and then this collector current is orders of magnitude greater than the base current, and is what make the BJTs be seen as current control amplifiers and current control current sources, right? This is why the bulk of the current goes from collector to emitter, and is due to that effect, right? So let's write that down. This collector current is orders of magnitude greater than the base current and is what makes BJTs be seen as current controlled amplifiers or current controlled current sources. Okay. Alright, and that is the story behind how BJTs work.